Hi everyone, in this video we are going to be investigating the electric field due to a uniformly charged rectangular plate, and specifically we're going to be finding the electric field due to this plate at a point such as the one labelled R in this diagram, which is either directly above or directly below the centre of the plate. Now you can sort of adapt and extend the method that we're going to use in this video to find the electric field due to any point, not necessarily a point on the axis. However, the maths involved very quickly becomes quite time-consuming and cumbersome, and I didn't think it would make for a very interesting video. So we're going to focus on the symmetrical on-axis case. And as you can see on the diagram, the key parameters of the problem are that the plate has a total charge of Q, uniformly distributed, and it has a length and a width of A and B. So the method that we're going to use is based on the principle of superposition. We can't use Gauss's law in this case because you can kind of see that the electric field is not going to have a nice symmetry as it does in the case of like a spherical charge or an infinite line charge or something like that. So we're going to split our charged plate up into infinitely many tiny pieces, and then we can treat each tiny piece as a point charge. In other words, it has an inverse square law field. And then we just sum up the fields due to each individual piece of the plate, and we'll get our overall field at the end. In order to make any progress on this, we've got to define some sort of coordinate system, and we may as well use a Cartesian coordinate system since we have a rectangle here. So for convenience, we'll place the origin of our coordinate system at the center of the plate. We're going to have our x-axis pointing to the right, our y-axis pointing perpendicular to that x-axis but in the plane of the sheet of charge, and then we'll have our z-axis pointing directly up towards the point at R. So let me just label those. We've got x, y, and z. Now, using this Cartesian coordinate system, our element, infinitesimal element of the plate is just going to be a little rectangle. So let me draw a particular element of the plate at some arbitrary set of coordinates. So it's going to look something like this. It's going to look like a parallelogram instead of a rectangle because we're looking at a 3D object in 2D space. Now, this little element is going to have a width of dx and a height of dy. It doesn't have any extent in the z direction because we're dealing with a flat plane here. So while we're setting up our element, another useful thing to define is going to be a vector going from the center of that element to the point that we're interested in, which is that lowercase r. Why don't we call that vector capital R? The reason why that's a useful vector to consider is that the electric field due to the infinitesimal element, the area element that I've just drawn, that electric field is going to be pointing along the capital R vector, right? Because it's going to be a radial field. So let's start making this a bit more quantitative and see if we can write down some initial expression for the electric field that we are aiming for. So we're trying to find the electric field vector E at the position R. I should also note, by the way, that R has coordinates 0 and 0 in the x and y directions and just z in the z direction. So let's begin by considering the contribution to the total electric field due to this little area element that we've drawn on. And again, we can treat the area element as a point charge because it's so small. So we expect it to have an electric field that behaves according to Coulomb's law. Now, Coulomb's law says that the electric field is proportional to the charge of your point charge. I'm going to call that dq because it's an infinitesimal bit of charge. We have to divide that by the constant 4 pi epsilon naught, and then the distance between the point charge and the point we're interested in squared. Now that distance is going to be the modulus of the capital R vector, so we've got to square that. And this electric field, contribution to the electric field, is going to point in the r hat direction, where r hat is a unit vector pointing in the same direction as this capital R vector in the diagram. Now, to get r hat, you can take the original r vector and divide it by its own magnitude. So what that means is instead of putting a hat there, I can just put the ordinary r vector and change this squared into a cubed on the bottom. So it kind of looks like it's an inverse cube law now, but it's not really, because remember, this r vector is not a unit vector. So that has a length of mod r itself. So that's the contribution to the electric field due to our infinitesimal charge element. So then all we have to do is sum over all possible charge elements in the plate. And when we sum over a continuous distribution like we have here, we basically just integrate. So all I have to do is put an integral sign there. So what can we actually do with this integral? Well, to start with, we can take out some constant factors In particular, there is a 1 over 4 pi epsilon naught that we can take out. What can we do with the dq? Well, if we're assuming that the charge is uniformly distributed, in other words, the charge density is uniform, then dq has to be proportional to the area of our infinitesimal element, right? The charge will be shared in proportion to the area. Now, the area of our little rectangular element is dx dy, and the total area of the big rectangle is AB, and therefore our infinitesimal element occupies a fraction of the area given by dx dy over AB. So if we take that fraction, dx dy over AB, and multiply it by the total charge q, that should give us the charge of our small element. So the q part I can put in front because that's a constant. The AB is also a constant. Our integral is now a double integral because we've got dx dy for our bit of area. And then the only thing that we have left inside the integral as part of the integrand is just mod r cubed and then the r vector itself. So before we proceed with the integration, let's just think about what we can learn from the symmetry of the problem. So notice that this integral, it's a vector expression because of the presence of that r at the end there. So it's actually 3 different integrals. But fortunately, we don't actually have to do 2 of them. You can see from the symmetry of the problem that the x and y components of the electric field are both going to be 0. I think there are 2 ways to understand why that is, really. One of them is to just look at the diagram, see that we are only interested in a point that's directly above the center of the plate, and then think, well, there's no special direction that the electric field should be pointing in, right? It would be kind of strange if the electric field sort of at the center of the plate decided to point slightly to the right. It just wouldn't really make any physical sense. Or you can take the slightly more mathematical viewpoint and imagine actually doing the integrals, summing up all the contributions from the various charge elements, and you can see that, for example, all of the charge elements on the left of the plate, their x components of their electric fields are going to exactly cancel with all of the x components of the electric fields from the right-hand side of the plate. And similarly, when you integrate over your y coordinate, the charge elements near the bottom of the plate are going to exactly cancel with the charge elements at the top of the plate, leaving you with only a z component of your electric field. So that brings us to the main part of the video, which is actually finding this z component of the electric field. It's called Ez, which is a function of the position r. This is a non-trivial integral to do, which is going to require various substitutions as we go along. So let's firstly just put that prefactor in front, q over 4 pi epsilon naught AB. And what are we going to integrate? Well, it's dx dy over mod r cubed times the r vector. Now, in fact, the r vector is a good place to start because the z component of that r vector is just going to be the z coordinate of the point lowercase r, right? To get from anywhere in the plane of the charged sheet up to the point that we're interested in, you just have to go up by a distance of z. Therefore, the r vector only contributes a z to our z integral, right? So the numerator of this integrand is z dx dy. The denominator is mod r cubed, right? And modulus of r is going to be x squared plus y squared plus z squared. And then that's to the power of a half, but then we cube it, and so it's to the power of 3 over 2, right? The modulus of r being the square root of x squared plus y squared plus z squared follows directly from Pythagoras' theorem in 3D. Now would also be a good time to think a little bit about the integration limits. So if you're integrating over the whole rectangular plate, your x coordinate is going from minus a over 2 up to a over 2, and your y coordinate is doing a very similar thing, going from minus b over 2 up to b over 2. We can make a bit of a simplification with these integration limits because notice that our integrand is an even function of both x and y, because x and y only appear as their squares. So if you flip the sign of x or the sign of y, then your integrand is not changed. And so because we're integrating an even function over a symmetrical range, right, from minus a over 2 to plus a over 2 and minus b over 2 to plus b over 2, we can just integrate from 0 to a over 2 and 0 to b over 2, and then multiply by a factor of 2 for each integral, in other words, for the x integral and for the y integral. So using that little symmetry trick does two things. Firstly, it basically makes the 4 from the prefactor disappear. So now we've just got q over, not 4, but just pi epsilon naught ab. Our integration limits are now 0 to b over 2 for the y direction and 0 to a over 2 for the x direction. And then the integrand itself is the same. Let me just copy all of that, and then we'll have a complete integral. There you go. It just turns out that having those slightly simpler integration limits is going to save us a lot of trouble later on when we use various trig substitutions to actually solve this. So what I'm going to do is call the integral part of this expression itself I. We don't really care about the q over pi epsilon naught ab until we put it all back together at the end. And so most of the video is going to be dedicated to finding the value of the integral I. One more thing we can do, in fact, is actually take this z out the front, because we're only integrating over x and y, and so z is actually a constant from the point of view of this integral. So let's do the x integral first. Order of integration doesn't really matter, everything is symmetrical, but let's just choose to do the x integral first. And to simplify the integrand, because we don't really care about y when we're integrating over x, we're going to introduce a new variable, which I'm going to call rho, and it's going to be defined implicitly by the relationship rho squared is equal to y squared plus z squared. Why am I putting this squared here? Well, I guess there are two reasons. One is that y squared plus z squared has to be positive, so it kind of makes sense to force the left-hand side to be positive as well. And secondly, we are going to end up doing a trigonometric substitution, and having the rho as a squared variable just makes things work out a bit more nicely. So when you incorporate that newly defined variable into your integrand, then I is going to be the double integral. I'm not going to bother writing the limits in every time to save a lot of unnecessary writing. It's the integral of dx dy over it's x squared plus this y squared plus z squared, right? That is just rho squared. So this is x squared plus rho squared to the power of 3 over 2. And let's just, for clarity, write that as sort of two separate integrals. So it's the integral with respect to y of the integral of dx over x squared plus rho squared to the 3 over 2. So we're going to do that x integral first. So as soon as you see x's that are squared and added to other squared variables, that should make you think of trigonometric substitutions, because there are loads of trig identities, well maybe not loads, but 3 trig identities that involve squared trig functions. And so in this particular case, the appropriate thing to do is to introduce another variable. We're going to say let x be equal to rho, which is a constant, remember, for the purpose of the x integral, rho times tan theta. So we're introducing this new variable theta implicitly. And when we do that by differentiating both sides, we find that dx is rho times sec squared of, sec squared theta d theta. And we get a very nice simplification, because x squared plus rho squared, what happens to that? Well, let's just write this out. X squared plus rho squared is going to be, you can factor out a rho, right? Because x itself is proportional to rho. So you get rho squared times tan squared theta plus 1. And 1 plus tan squared is sec squared of theta. That's the trig identity, standard trig identity. And so it's rho squared times sec squared of theta. So then let's plug all of that into our integral I. The I is now the integral with respect to y of the integral of, well, the top is just dx, but dx is rho sec squared theta. I didn't derive that, by the way. I'm just quoting the standard result for the derivative of tan theta. So the numerator is now just rho times sec squared theta times d theta. The denominator, which was x squared plus rho squared to the 3 over 2, it's rho squared sec squared theta to the power of 3 over 2. And when you do that to the power of 3 over 2, the squareds just basically become replaced by cubes, right? So the denominator is now rho cubed times sec cubed of theta. And then a lot of stuff is going to cancel down, right? So this simplifies to the integral with respect to y of the integral of 1 over rho squared, right? Because you had rho over rho cubed. And then you're going to have 1 over sec theta, because 2 powers of sec theta cancel down, and 1 over sec is just cos, so we get cos theta d theta, which is a pretty easy thing to integrate. Cos just integrates to sine, right? So I'm going to write that as the integral dy of 1 over rho squared sine theta. This sine theta is really evaluated between two limits, but instead of figuring out theta limits, I'm going to transform back to our original variable x and then put the limits in terms of x. So let's not worry about the limits at this stage, but we first transform back to x. Now, what can we do with our sine theta? Well, we can do some more trig identity stuff. Sine theta is cos of theta times tan of theta. The reason this is useful is because tan of theta is directly related to x. Another way of writing that is that it is tan theta over sec theta, because sec is 1 over cos. And this is, again, a nice thing to do because sec is related to tan, because tan squared plus 1 is sec squared. And so we can write that as tan theta over the square root of 1 plus tan squared of theta. Then we use the fact that x is rho tan theta to substitute for tan theta in terms of x. So the numerator is just x over rho. The denominator is the root of 1 plus x squared over rho squared. Then I'm just going to multiply the top and bottom by rho, and so you get x over root of rho squared plus x squared. So that is sine theta, which appeared after we did our integration in terms of x. It's x over root of rho squared plus x squared. So let's substitute that x expression in place of sine theta. Sorry. So we've got the integral dy 1 over rho squared x over root of rho squared plus x squared. Now we can put our limits in because we transformed back to x, right? And the limits that we had in our original integral I were just 0 and a over 2. So I put 0 there, and I put a over 2 there. And we still have to integrate with respect to y. We haven't done that yet. So I put integral dy 1 over rho squared. Now, when we substitute a over 2 in, the top is just a over 2 now, and on the bottom, it's going to be rho squared plus a squared over 4, and then we're going to subtract 0, basically, because when we put x equals 0, the whole thing disappears. So because we now need to integrate over y, we've got to write this rho squared back explicitly in terms of y, which is y squared plus z squared. I'm also going to take out this constant factor of a over 2. So I is now a over 2 times the integral of, well, let's just put dy on the top. It's going to be over rho squared, which is y squared plus z squared. And then we've got the square root of rho squared, which is again y squared plus z squared, plus a squared over 4, whole thing square rooted, and there we go. Now this is a much more complicated looking integral than the x integral that we did to start with, but you've still got variables that are squared and added to other squared variables, which suggests that we could do it using a similar method, at least using trig identity. So let's try to proceed in the same way and see what happens. So the first thing we could do, as we did last time, is introduce another variable. Let's call it sigma because we already used rho. So let's say sigma squared is going to be defined as all of this stuff here, z squared plus a squared over 4, which remember is a constant from the point of view of doing an integral over y. So let's say sigma squared is z squared plus a squared divided by 4. Just quickly rewrite our integral. So it's a over 2 times the integral dy, and we've got over y squared plus z squared, and now the square root of y squared plus sigma squared. So the fact that we've now got this y squared plus sigma squared suggests a tan substitution again. So let's try that. Let's introduce another variable, transform our integral, and say that y is equal to sigma times tan of phi. We already used theta before, so let's call it phi. Again, by exactly the same reasoning as we did with our first integral, dy is going to be sigma sec squared phi d phi, and y squared plus sigma squared, using the identity 1 plus tan squared is sec squared. That's going to be sigma squared times sec squared of phi. Then we can substitute all of that stuff into our integral and see what happens. So we've got a over 2 integral of, okay, dy over something, or in fact, we don't even want to write it as dy anymore, do we? We want to write it as sigma sec squared phi d phi. So on the top, we've got sigma sec squared of phi d phi. Then on the bottom, you have y squared plus z squared to start with. So just directly sub in our y, which is sigma tan phi. So sigma squared tan squared phi plus z squared. Then we've got the square root of y squared plus sigma squared, which is the square root of, according to this identity down here, the square root of sigma squared sec squared phi, which is just sigma sec phi. So let me put that there. Sigma sec phi. And then at least some stuff cancels from both the top and the bottom. So this is now a over 2 integral of sec phi d phi, because 1 power of sec cancelled and the sigma is also cancelled, and the bottom is just sigma squared tan squared phi plus z squared, which at least looks a little bit simpler than what we started with. However, from here, the next step is not really obvious, and there might be different ways to proceed. I'll show you what I did after playing around with various trig identities. What I found worked was to multiply the top and bottom by cot squared of phi, in other words, 1 over tan squared phi. That turns it into a over 2 times the integral of, well, straightforwardly on the top, it's just sec phi times cot squared phi d phi. The bottom is then sigma squared, because, well, tan squared times cot squared is just 1 by definition, and then plus z squared cot squared of phi. You can then use more trig identity to simplify the numerator a little bit. Let's do that over on the right hand side here. So the numerator is sec phi times cot squared of phi. Let's just use the definitions of sec and cot. So sec is 1 over cos, so we've got 1 over cos phi, and cot is cos over sine, so we've got cos squared phi over sine squared phi. One of the powers of cos cancels down from the top and the bottom. And then what do you have remaining? You've got cos over sine squared. The cos over sine can be turned into a cot, so let's put cot phi there, and then you've got an extra 1 over sine, extra power of sine at the bottom, which is the same as cosec. So cot phi cosec phi, that's our numerator. Not the simplest looking thing, but at least we don't have the squared that we had initially. So let's put that in and then think about what kind of substitution would be helpful. So it's a over 2 integral of cot phi cosec phi d phi over sigma squared plus z squared cot squared phi. Now, depending on how familiar you are with derivatives of trigonometric functions, the numerator of our integrand is now a bit of a giveaway as to a potentially useful substitution, which I'm going to write down here. We're going to let u be equal to cosec of phi. The reason why that is useful is that when you differentiate cosec phi, you get minus cot phi times cosec phi. And we've got our d phi there as well. And this cot phi cosec phi is exactly what you see on the top there. So that's a bit of a hint that the substitution u equals cosec phi might be useful. Again, I'm not proving that that's the derivative of cosec phi here, but you can do it pretty straightforwardly using the fact that cosec is defined as 1 over sine phi, and then you can use the chain rule to get that result. Okay, so let's apply that substitution in terms of u. You still have this a over 2 factor out the front. Cot phi cosec phi d phi is minus du, so the numerator is now minus du. How about the denominator? Well, we've still got our sigma squared there. We've still got our plus z squared. We can use the identity that 1 plus cot squared is cosec squared, and therefore cot squared is cosec squared minus 1, which here means u squared minus 1, right? So this cot squared of phi is just u squared minus 1. If we expand those brackets, we just get a over 2 integral of minus du over z squared u squared plus sigma squared minus z squared. But then we can go back to the definition of sigma squared, right? That so-called thing up there, which is z squared plus a squared over 4. And therefore sigma squared minus z squared is the same as just a squared over 4 by definition of sigma. So this is now a over 2 integral minus du over z squared u squared plus a squared over 4. It's looking simpler and simpler. Okay, I've just had to clear a bit of space so that we can continue our working. But let's get on with this simplification. We can also make this look a bit nicer by taking out that z squared and writing this as a over 2z squared integral of minus du over u squared plus a squared over 4z squared. Now that's a fairly standard looking trigonometric integral. You can do it using a tan substitution. So we could introduce a new variable, could call it alpha, and say that u is equal to a over 2z times tan alpha. That would work. However, it's going to turn out to be a little bit easier because of this minus sign here. It actually turns out to be a little bit easier to do it using cot this time, although we used tan before, right? So just because of that minus sign, I'm going to change my variables yet again and say that u is now equal to a over 2z times cot of our new variable alpha. Again, using standard trigonometric derivatives, we find that du is minus a over 2z times cosec squared of alpha d alpha. When we substitute all of that in, we've still got our a over 2z squared prefactor. The numerator, which is minus du, this is why this is a good substitution. Now the minus sign is cancelled because du itself had a minus sign, right? So the numerator is now just plus a over 2z cosec squared alpha d alpha. The denominator is a squared over 4z squared times cot squared alpha plus 1. And then we use another trig identity. 1 plus cot squared is cosec squared. So that cancels with that. And then you're basically just integrating a constant, right? You've got a over 2z squared. Then your integrand is just a over 2z divided by a squared over 4z squared. And that simplifies, I believe, to just 2z over a. So 2z over a, and then you've just got the integral d alpha. A lot of stuff nicely cancels. The 2's cancel, the a's cancel, one of the z's cancels as well. And so you are just going to get 1 over z times alpha. Again, I'm not going to bother writing in the plus c constant or whatever, because we are evaluating this between two limits, but we want to first transform back to our original variable that we're integrating over, which is y, right? So I'm going to leave off those limits until we have transformed back to y. So what can we do with this? Well, we've got 1 over z. Alpha, we can use the definition of alpha, right? U equals a over 2z cot alpha, to write alpha in terms of u as a starting point. So we've got inverse cot of 2zu over a directly from that definition. So we're getting closer. Now we've got it in terms of u, but we want it in terms of y. To go from u to y, you can combine two of the lines from this bottom right-hand corner here. So y is sigma tan phi, and u is cosec phi, right? We can use those combined with the trig identity to get u directly in terms of y. So notice that u squared is 1 plus cot squared phi, because 1 plus cot squared is cosec squared. This is a good thing to do because cot is just 1 over tan, And then from this equation here, we can relate that back to y. So we can say u squared is 1 plus, it's going to be sigma squared over y squared, right? Just directly from that equation. So 1 plus sigma squared over y squared. You can even write that as a single fraction as just y squared plus sigma squared over y squared. Then we just take the square root of all of that stuff and substitute it in place of the u that we've got there. So that's going to be 1 over z times inverse cot of 2z over a. And then we get the square root of y squared plus sigma squared all over y. And then what we're going to do to get this in terms of our original variables, remember sigma wasn't actually one of the parameters of the problem, right? Sigma squared is z squared plus a squared over 4. So we want to put that back in. Let's do that. It's 1 over z times inverse cot of still 2z over a. Now it is going to be the square root of a squared over 4 plus y squared plus z squared, just plugging back in the definition of sigma squared. That's all over y. At this point, we've got an expression that is in terms of y instead of the variables that we substituted later on. So we put our limits back in, and the limits of the original integral I in terms of y was just 0 and b over 2. So I put 0 there and b over 2 up at the top there. Now let's substitute those limits in. We've still got 1 over z inverse cot of 2z over a. Plugging in y as b over 2 is pretty straightforward. We just get the square root of a squared over 4 plus b squared over 4 plus z squared, and then we divide the whole thing by b over 2. What about when we substitute 0? Well, as y approaches 0, the argument of your inverse cot approaches infinity. And if you consult a graph of inverse cot, you'll see that it tends towards 0 as your argument tends towards infinity. So we're doing inverse cot of infinity, which is in fact 0, and so we just subtract off 0. That doesn't contribute anything. And so we're almost at our final result. So we've got, at the moment, 1 over z times inverse cot of, let's clean this up a little bit, because we divided by b over 2, the 2 here is going to combine with the 2 here and make a 4. So we've got 4z over ab, and then we've got this square root bit, right? The square root of a squared over 4 plus b squared over 4 plus z squared. There are just 2 more things I would want to do with this expression to make it look a little bit nicer. One of them is get rid of these fractions. So you take out a factor of a quarter from this the square root, which is really a factor of a half because you're square rooting it. So you've got 4 here, and you're multiplying that by a half, and then all of the stuff under the square root is going to get multiplied by 4. So the result of that is you get, as your argument, it's now 2z over ab times root of a squared plus b squared plus 4z squared. The other thing I would do, which is kind of optional, is to note that generally we're more familiar with inverse tan than inverse cot, right? So you can use the fact that inverse cot of some argument is the same as inverse tan of 1 over that argument, right? That pretty much follows from the definition of cot in terms of tan. So you can flip the argument upside down and change your cot into a tan, and you get 1 over z times inverse tan or arctan of, now your AB is on the top, and your denominator is 2z root of a squared plus b squared plus 4z squared. Now all we have to do is go back to the fact that I was not the full electric field. We have to multiply the whole thing by this prefactor qz over pi epsilon naught AB. So you get that your electric field, let's put it back in vector form as well. So your electric field at this position z is going to be your prefactor q over 4 pi epsilon naught AB. What happened to this z? Well, it's going to cancel with this 1 over z when we multiply it by I. Then I'm going to get this inverse tan factor. Let's see if I can just copy and paste that. So that's the contribution of the integral I, and then we can just put that in the z hat direction to turn it into a vector. So this is, of course, a pretty complicated looking expression for our electric field. It's kind of hard to just look at that and get a feeling for what it means. So to help with that, what I'm planning to do in my next video is consider 3 interesting special cases or limiting cases of this electric field. And we'll see how this expression, complicated expression, relates quite nicely to 3 different more commonly known electric fields in electrostatics. So congratulations to anyone who made it through all of those trig substitutions. I hope it was all worth it for that result, and I will see you soon to go through those limiting cases.